Let's say that I am given this bent member that has a distributed load of 20 pounds per foot acting along the vertical portion. And then at point B, which is in the middle of the horizontal member, I have a positive 160 pound-foot moment. The entire system is 6 feet wide and 8 feet tall. I have a roller at A that is acting at a 20-degree incline and a pin at C. Find the reactions at roller A and pin C. Our solution is going to start with the free body diagram. So I'm going to draw the entire bent member here. And starting with my reactions, I have a pin at C, which means I have CY and CX. And I have reaction A that is acting perpendicular to the surface. So if the surface is inclined at 20 degrees, that means I'm acting perpendicular to that, which means that I am 20 degrees from the vertical. And I'm just going to call this reaction A. And then I have a distributed load. So my distributed load is going to have a resultant force that is equal to the area under the load. So that is 160 pounds. And it is acting at 4 feet from A. So that would be what I call the X bar. All right, and then we have our 160 foot-pound moment acting about B. So now that I've got my free body diagram established, I can sum for my forces in the X direction, and I will need to break apart reaction A into its vertical and horizontal components. So this would be reaction AX and reaction AY. Reaction AX would be negative because it's pointing to the left of the magnitude reaction A, and then the horizontal component sine of 20 degrees. And then I would have my 160 pound resultant force for the distributed load. And then I would have CX. By the way, X and Y. Then I would sum for forces in the Y direction, because that doesn't get me anywhere. 2 unknowns, 1 equation. And I would have AY, so that is reaction A, and that is adjacent to the angle, so that is cosine of 20 degrees. And then I will need plus CY. 2 unknowns and 1 equation there. So now I've got a total of 2 equations, 3 unknowns. So last, I'm going to sum my moments about A, and I'm going to add counterclockwise. So that's going to give me 0 is equal to, let's see, that's going to be 160 pounds acting at 4 feet, and that is causing a clockwise rotation about A. I have the moment itself, 160 pound-feet acting counterclockwise. And then I have CY acting at a distance of 6 feet from A horizontally, vertical force, horizontal distance, and that is also counterclockwise. And then I have CX acting at a distance of 8 feet, and it will be clockwise. Okay, again, horizontal force, so I need the vertical distance. So now I have 3 equations and 3 unknowns, and I'm going to solve this with a matrix. Sine of 20 degrees is going to be negative 0.342. CX is going to be 1, CY is going to be 0, and my constant is going to be negative 160. So the order of my coefficients is going to be reaction A, CX, and CY. So there's my coefficient matrix. My variable matrix, back to the coefficient matrix, moving to force Y, I have cosine of 20 degrees, 0.9397, Cx is 0, and Cy is 1. And I have a constant of 0. And then my last moment equation, let's see, my reaction at A is going to be 0, Cx is negative 8, Cy is positive 6, and its constant is going to be positive 480. So now I have my matrices here. Times is equal to this. So if this is what I would call matrix A, and I would call this matrix X because it's the variables, and you are matrix B, what I'm going to plug into my solver is matrix X is equal to the inverse of matrix A times matrix B. And we will find that my reaction at A is equal to 95.5 pounds, and that ended up positive, so that meant my assumption is correct. It is acting 20 degrees from the vertical. My reaction Cx is equal to 127.3 pounds, and I got that to be negative, so I need to switch my sign to the left, and my reaction Cy is equal to 89.8 pounds, and I also got that to be negative, which means I need to switch my sign and it needs to act down. So let's say that I am given a propped cantilever. It's propped because it has a roller at A and a fixed end at B. The fixed end makes it a cantilever, and it's propped because of the roller. I have an evenly distributed load across the entire thing and an applied moment at A. What's unusual about this problem is I have an internal pin at C instead of the external ones that we've been looking at. I want to find the reactions at roller A and fixed end B for this system. I am going to start with my free body diagram. So roller at A has a vertical reaction, AY. Fixed in B has a vertical reaction, BY, a horizontal reaction, BX, and a moment reaction, moment B, assuming that X is horizontal and Y is vertical. Right now, don't worry about internal hinge C. I also have a distributed load that I need to show as a resultant force. So I'm going to find the area under that curve, and that is 30 times 14 meters. That is 420 pounds. So this is force resultant, and it acts at a distance of 7 meters from A. And then of course I have my moment load, 120 Newton meters, 420 newtons. Good job. I can use my equilibrium equations. Some forces in the x direction are equal to 0. 0 is equal to bx. So that one's solved. Some forces in the y direction. And I have AY minus 420 newtons plus BY. So there is two unknowns because my BX is solved for. And then I sum moments about A. And remember, moment couples are always in the equation. So that 120 Newton meters is there. It's counterclockwise, so it's positive. And then AY acts at A, so there's no distance, no moment. Then I have resultant force, 420, and it acts at 7 meters from A, and it's causing a clockwise rotation. And then I have BY that acts 14 meters from A, and it has a counterclockwise rotation. And then I have the moment at B that is also counterclockwise. So I have two forces and distances that are causing moments, and then two moment couples that are applied to the system that are in there. BX has no vertical distance from A, so it does not create a moment. All right, 3 unknowns, 2 equations. What next? Well, I can actually take this system apart at C, free body diagram, AC, because C is a pin. So if I take it apart at C, then I'm going to have a vertical and horizontal reaction at C, just like I would for an external pin. I still have my AY reaction here, and I still have my applied moment, 120 Newton meters. Okay, now I also have the distributed load coming all the way back up here. This distributed load is over the entire system. So if I'm looking at part of the system, then I need to look at part of the distributed load. So I'm going to have a new resultant force that is the 30 times 6 meters, so that's 180 newtons for my resultant force, and then it acts at 3 meters from A. So I have an all new free body diagram. Yay! Summing for the forces. Well, you know what? All I need is the reaction AY. And the quickest way to do that is to sum moments about C. That'll take care of my two unknowns at C because they have zero distance, so they do not create a moment. So I'm going to have my moment couple, 120 Newton meters. I'm going to have AY acting at 6 meters, and it causes a clockwise rotation. And then I have my force resultant, 180, acting at 3 meters. That causes a counterclockwise rotation. And I have one unknown, one equation. AY is equal to 110 newtons, and it ended up positive. So my assumption is correct, and it is acting up. Now that I have AY solved for, I can plug it in up here, and that will give me BY, which will equal to 310 newtons up, because it ended up positive, so that means my assumed direction is correct. And I can plug in BY here, 310, and we find that our moment reaction at fixed end B is equal to 1,520 Newton meters. This value ends up negative, which means I need to switch my assumed direction and make it clockwise. Okay, so now I have all 4 of my reactions solved for.